The last three videos on this playlist were about complex integration. And the next three videos, starting from this one, is going to be about series and local behavior. Still talking about complex numbers, definitely. So here we are talking about power series. So under the broad concept of series and local behavior. So let's go on to talk about power series. Now, as we're talking about analytic functions and all that, we got to a point where we saw the link between analytic functions and being able to express such functions in series form with a radius of convergence that is infinite. So here we look at power series. Interestingly, I have other playlists where I have talked about. I think I have a whole playlist dedicated to power series itself, like that. But here, this is power series as it connects with the concept of complex numbers. So power series centered at Z naught is actually the summation from n equals 0 to infinity of an into z minus z naught raised to power n. An here is actually a complex constant, and then z is a complex number, and of course z naught is also complex, and it is the center of the series. So a special case is when it is centered at zero, meaning that z naught is equal to zero. So in that case, the z naught disappears, and we just have a n z raised to power n. So this is a power series centered at z naught equals zero, centered at zero. So summation from n equals zero to infinity of a n z raised to power n. Now we move on to convergence of power series. So there's a fundamental theorem in that regard that there exists R, which belongs to the closed interval 0 to infinity. That means R can take values from zero. It can take values from 0 to infinity, such that the series converges absolutely if the absolute value of z minus z naught is less than the radius, is less than R. So of course it is the radius. Then the series diverges if the absolute value of z minus z naught is greater than R. So a convergent series is that series whose absolute value for which the absolute value of z minus z naught is less than the radius. Then a series will diverge if the absolute value of z minus z naught is greater than R, which I'm sure is the radius. And then behavior on absolute value of z minus z not equals r must be checked separately. So in any situation where the absolute value of z minus z naught is actually r, then it must be checked separately to see what exactly the issue is. So for region of convergence now, so that's what this is about. Region of convergence is given as the absolute value of z minus z naught less than r. So this is a disk in the complex plane. This is a disk in the complex plane. So, and of course, a disk looks something like this. Uh, is it this? Then you have the center here, so you have something like this. You have Z not here, and this is Z right here. Hmm. So we have that. Then we talk about the radius of convergence. So to to check for the radius, right, we have different kind of tests. Like we have the root test called the Cauchy-Hadamard formula, and that tells us that R is equal to 1 all over the limits of the supremum of the square root, the nth root rather, of the absolute value of an, whatever an is, and as n goes to infinity. So that gives us the value of r there. Then for ratio test, if the limit exists, then you look for the limit of the absolute value of an over an plus 1 as n approaches infinity. So to find the radius of convergence. So, and then the geometric interpretation of that would be that the region of convergence is a disk. We have center at z naught and the radius is r. So just like what I showed here the other time, you have the center here, and then this is the radius. Okay. So, and we are saying that if the absolute value of z minus z naught is less than the radius, right, then we say that the series that gives that actually does converge. So this differs from real analysis where convergence is typically on intervals. So convergence here is not on interval, it's based on this concept we have here. So talking about a geometric series, so we have the summation from n equals 0 to infinity of Zn. This is a geometric series. Of course, an here is automatically 1. That's what that means. So for a geometric series, a geometric series is actually a power series whose center is at 0 and then an is 1. So in that case, like I demonstrated in a previous video, that the summation of Zn is actually the same thing as 1 over 1 minus z. For absolute value of z less than 1, that is, z must lie between -1 and 1. And then the radius of convergence in this case is r equals 1. So to reenact that concept that I talked about, so, you have summation from n equals 0 to infinity of z raised to power n, right? That means you have z raised to power 0 plus z raised to power 1 plus z raised to power 2 plus z raised to power 3 and so on and so forth. That means you have z raised to power 0 is 1, then plus z squared plus z raised to power 3 and so on and so forth. So that's what you have there. But so now this is a geometric progression. This follows geometric progression, as you can see. And the reason is because from the first term, if we have the first term, so the first term, right, if we call that A, which is 1, then we have a common ratio. That means we have a constant number multiplying to get the next term. So if the common ratio is r, not the big R now, so that's like z over 1, or if you like z squared over z, or z cubed over z squared. In short, that's simply z. That's a common ratio. So you have a is 1, r is z. So since it's a geometric progression now, you can then use a geometric progression formula. You know that there's something called the sum to infinity, which is given as s infinity equals the first term over 1 minus the common ratio. So the first term here is 1 all over 1 minus the common ratio is z. And that is why we can say that the summation of z raised to power n from n equals 0 to infinity is the same thing as 1 over 1 minus z. Like that. So you see the connection between geometric progression and um and this concept of series, power geometric series. So radius of convergence here is actually 1. Okay, so we then have geometric exponential series. I haven't considered geometric series. For the exponential series, right, we have summation from n equals 0 to infinity of z raised by n over n factorial. So if you use the ratio test, so here an is 1 over n factorial, right? So absolute value of an plus 1 over an is actually absolute value of z over n plus 1, which goes to 0 as n approaches infinity. So convergence happens for all z. And the radius in this case is r, which is equal to infinity. This series represents e raised to power z. So, by the way, you remember this ratio test, right? In case you're wondering what the ratio test we have done here is like, generally speaking, you know that it's a general kind of series is summation from n equals 0 to infinity of an zn, like that. That's all we have. But for an exponential series, we now have this expression you have now. We have a summation from n equals 0 zn over n factorial. Okay, so that's a summation from n equals 0 to infinity z raised to power n over n factorial. If you rewrite this is like summation from n equals 0 to infinity. Okay, let me uh space it out. Summation from n equals 0 to infinity 1 over n factorial, then you have Zn like this. So if you want to compare it with that now, so you can say that a sub n is actually 1 over n factorial, right? So this is like a sub n. So if you need a sub n plus 1, that would be 1 over n plus 1 factorial. So if you now want to do the test, if you want to do the ratio test, so ratio test is such that you have a limit as n goes to infinity for the absolute value of an plus 1 over an, an plus 1 over an like that. So you have an plus 1 over an, and that means you have limit as n approaches infinity, for an plus 1 is 1 over, that's 1 over n plus 1 factorial. Then an is 1 over n factorial. So that means we have limit as n approaches infinity for 1 over n plus 1 factorial divided by 1 over n factorial. So we have limits as n approaches infinity for 1 over n plus 1 factorial times n factorial over 1. So we can uh, break things up here. Limit as n goes to infinity. So you have 1 over n plus 1 factorial is n plus 1 times n factorial, and then multiply by n factorial over 1. So this cancels this, so that we then have limit as n goes to infinity for 1 over n plus 1. Okay, so if that is the case, that's limit as n goes to infinity for 1 over n plus 1. So that means if you put n for infinity, infinity for n, so you have 1 over infinity plus 1, and that is 1 over infinity plus 1 is infinity, and 1 over infinity is 0. And because that's coming from the concept that x over 0 is undefined. So if you put this over 1 and cross multiply, it means 0 infinity is x. If you divide through by infinity, it means this cancels. So x over infinity divided is equal to 0. So anything divided by infinity is 0. So here now we see that because this is 0, uh, it means that the radius of convergence is less than 1, right? So, and we can say that, oh, yeah, it's less than, it's undefined actually. The radius of convergence is undefined. But because we got 0 here, that we say that the series converges. So series converges, right? So the series converges because this 0 is less than infinity. Okay, so now this particular exponential series represents e raised power z. This is another way, this is another expression for e raised power z, actually. So for example 3 now, we have the summation from n equals 1 to infinity of z raised power n over n. So this is almost looking like the exponential series, but it is not, because this is not n factorial. So if you do the ratio test, we end up getting, so as n, okay, for here now we divide through, if you take the limit, divide through by n. So we have 1 over 1 plus 1 over infinity. 1 over infinity here is equal to 0. So we have 1 over 1. So that means absolute value of z goes to this approaches absolute value of z, unlike this one that would approach infinity, because uh the expression. Okay, I mean, this whole thing goes to 0, actually. This whole thing goes to 0, right? But in this case, the whole expression goes to the absolute value of z goes towards the circle itself. So this converges when the absolute value of z is less than 1. And that means that the radius is actually 1. So here, because this one goes to 0 now, that makes the radius to be equal to infinity, like that. So we then go to example 4, where we have n factorial over 2 raised power n, z raised power n. So here an is n factorial over 2 raised power n. So if you want to do ratio test, an plus 1 will be n plus 1 factorial over 2 raised power n plus 1. So if you carry all of that out, you have an plus 1 over an, that will be n plus 1 over 2. So as n approaches infinity, the function is undefined. And if the function is undefined, so it converges to the fact that z itself is 0. Okay, so that the whole thing goes to infinity. So convergence only occurs at z equals 0 in that case. So the radius then is actually 0, like that. So this is the logic. You do the ratio test, whatever value you get for that. So you can whatever value you get. So we've seen a constant thing going on here, that this goes to 0 if you divide z, uh if you divide something by 0, you get infinity. That gives the radius of convergence. And here it goes to z. So because this goes to z now, so we have 1 here. And then for this one, now because we have infinity, it's like something divided by infinity, you get 0. And the radius of convergence is 0. So in this case now, we have this expression here, just representing the power series So z s equals z raised to power n, and then we try to look at it for z equals 0.5. So we have this convergence of some z raised to power n. Of course, we can actually make this better by you know, put use f string and put dollar signs around this. Let's see if that changes, gives a better outlook. So here we have partial sums of all this, as you have n from 0 to 50, and you have the partial sums from 0 to 1000, like this. So this is what we see in this place. Talking about z raised by n. So you see, it looks better now with z raised by n here. Then we have boundary behavior. So even if r is equal to 1, behavior at absolute value of z equals 1 actually varies. So example is at z equals 1, we have divergence for harmonic series. If z is 1, we have 1 raised by n, which is 1 over n. So then at z equals minus 1, we have convergence, and this happens for alternating series. So the conclusion is that boundary must always be checked separately. So for every series, you need to check the boundary separately. So absolute value of z less than 1, that's a radius of convergence is 1. But when absolute value of z equals 1 itself is another kettle of fish. So you have to check to be sure. So we talk about absolute convergence, that inside the disk, the absolute value of z minus z naught is less than r. The series converges absolutely if this happens. So on the boundary, it may converge, it may diverge, and it may converge conditionally. So we need to check this behavior, this happening. So inside the radius of convergence, you can different. That's talking about differentiation of power series now. D dz of summation from n equals 0 to infinity of a n z minus z naught raised to power n. Of course, if you differentiate this now, you bring down the power, differentiate inside, that gives 1, and then you reduce this power by 1. So that gives us, because we are differentiating, I shift the summation one step. So we have summation from n equals 1 to infinity of n a n z minus z naught n raised to power minus 1. So power series are infinitely differentiable. They are analytic, like that. Okay. So in summary, we have that if you have a region, the result is that the absolute value of z minus z naught is less than r. If you have a shape, the shape is a disk. The region is given as this. The shape is a disk. The convergence is absolute inside. The boundary, you must test what's happening at the boundary, because it's possible that at the boundary you have convergence, divergence, or a conditional convergence like we saw just now. Then differentiability is infinite, and the radius r, you can use ratio or root test to confirm what the radius r looks like. Then the key idea is that power series in complex analysis always converge in a circular region, like that. So we have practice problems. Let's see. So you have questions 1 to 5 here. So questions 1 to 5 here. Then you have 6 to 10, 6 to 10 here. Then you have, okay, I think that was too far. 6 to 10, 11 to 15, and then 16 to 20. So I'll be solving two as usual. So um, let me see the two I'll be dealing with. Yeah. So this is power series right here. So I'll be taking questions 8 and 10. 8 is this: determine the radius of convergence, summation from n equals 0 to infinity of n factorial z raised to power n. So that means an is n factorial. Then we have problem 10, which is okay, this one n factorial by n raised to power n z raised to power n. That looks a bit trickier, but let's see how we can take care of that. So let's go for problem 8 now. Problem 8. Okay, I was writing like infinity. Problem 8. We want to the radius, find the radius of convergence of summation from n equals 0 to infinity for n factorial z raised to power n. So that's what we want to do. So um, first we can use the ratio test. Using the ratio test, So from here alone, we have summation from n equals 0 to infinity n factorial z raised to power n. That tells us that an is n factorial. So we are going to have an plus 1. That will be n plus 1 factorial because we're dealing with an plus 1 now. So that means we have solution summation of an plus absolute value of an plus 1 over an, which is equal to absolute value of n plus 1 factorial all over n factorial. So that means we have n plus 1 factorial is the same thing as n plus 1 times n plus 1 times n factorial and all over n factorial. So this cancels out. And then we have n plus 1. That's absolute value of n plus 1, which is equal to n plus 1. So having done that, we can then multiply. So you now multiply by absolute value of z. So that means we have n plus 1 multiplied by the absolute value of z. So if we take the limit as n approaches infinity for n plus 1 multiplied by the absolute value of z, you know. So this actually is equal to infinity for any z not equal to 0. For z equals 0, then it goes to 0. But for any other z, because n plus 1, if you substitute infinity here, so this goes to infinity. Infinity multiplied by this will go to infinity. So that approaches infinity. So in essence, you are saying that the limit of as n goes to infinity, okay, I mean that's done already, right? It's infinity, right? In that case now, we can say the series, the series diverges. The series diverges for all z that is not equal to 0 because of the infinity we got here. So since the series diverges like that, so the final answer, therefore, 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 it only converges at z equals 0. There and then the radius, the radius of convergence, the radius of convergence is r equals 0. So this is more like anytime you get infinity here, then the radius will be 0. So that's problem 8. So let's do problem 10 now. Problem 10. So for problem 10, we want to find the radius of convergence of summation from n equals 1 to infinity for n factorial over n raised to power n z raised to power n. Okay, so again, we want to use the ratio test. Using the ratio test, we know already based on if you compare summation from n equals 0 to infinity with of zn, right? If we compare that with summation from n equals 1 to infinity, n factorial over n raised to power n, z raised to power n. So if we compare these two, right, we can we see clearly that an is n factorial over n raised to power n. So as n approaches infinity, which of these will grow faster? That's one thing we may want to consider, but let's see. Let's go gradually. So if an is n factorial over n raised to power n, it means that an plus 1 would be, everywhere you see n, it becomes n plus 1. So you have n plus 1 factorial all over n plus 1 raised to power n plus 1, like this. So the ratio test then is this. We have uh, an plus 1 all over an, and that is so an plus 1 now is this expression here. So that's n plus 1 factorial, all over n plus 1 raised to power n plus 1. All of that divided by an is n factorial all over n raised power n. So we have to work with this carefully. So this is n plus 1 factorial all over n plus 1 raised power n plus 1 times n raised power n all over n factorial. Okay, if we try to tidy this up, then we get that okay, if we try to tidy this up, we know that this is n plus 1 times n factorial all over n plus 1 raised power n plus 1 times n raised power n all over n factorial. This cancels this so that we then have okay, so n plus 1 has some bearing with this. So we can have that this is I want to be careful here. This is n plus 1, n raised power n all over n plus 1, n raised power n plus 1. So now try to simplify. Hmm, trying to simplify now. Okay, we know also that this is n plus 1 raised power n raised power n all over. So this n plus 1 raised power n plus 1 is like n plus 1 multiplied by n plus 1 raised power n. Clearly, so this cancels this. So we then have n raised power n all over n plus 1 raised power n like this. So we can then say this is the same thing. So now we are still dealing with an plus 1 all over an, right? So this is the same as n over n plus 1 all raised power n. So if that is the case now, if we take the limit, so limit as n goes to infinity for an plus 1 all over an is actually the limit as n goes to infinity for n over n plus 1 raised power n. So that is simply going to approach e raised power minus 1. That's 1 over e. So that's e raised power minus 1 roughly. So if that is the case, we can now apply the ratio test. So now we can say that the limit of the absolute value of an plus 1 all over an multiplied by z, is equal to, so this whole expression is e raised power minus 1. So we have e raised power minus 1 times absolute value of z. So that means we have the absolute value of z all over e. So, and the absolute value of e, so from this now, convergence, this for convergence to happen, so convergence requires that that ratio should be less than 1. Convergence requires that the absolute value of z all over e should be less than 1. So if that is the case, it means that the absolute value of z now is less than e. So, and if that is the case, this automatically becomes our radius of convergence. So radius rather, sorry, the I think okay, I was going to say radius and ratio together, so it came out as ratios. So the radius of convergence is r equals e in that case. So with that, we come to the end of this interesting video about power series as far as it relates with complex numbers. Don't forget to check out how well you can handle the practice problems. So here we have 1 to 5, like I showed the other time, 1 to 5, then 6 to 10, then 11 to 15, then 16 to 20. And that's what we've got. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you have not subscribed, the question is, what exactly are you waiting for? Why not go ahead and subscribe right away and hit the notification bell also, so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you special privileges like seeing some videos before others see them, or being the only one to see certain videos because as you know, you just see those videos exclusively. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.